Now one end of spring is connected to wall, the other end is what I'm holding. So I think everyone knows, you just take the pen, in the pen there'll be some sort of a spring will be there, no? That is what the spring what we are going to discuss. Or for the cycle stand for vehicles, there you see that particular spring, no? That is what we are going to discuss here. So initially there's no elongation or compression, and what is the state of block is attached. Now external agent will come, and what he is going to do, he is going to pull the block. I'm going to pull the block here. Slowly from rest to rest I'll pull it. Then how much it got elongated? Say by x1. Okay, timing, let me say x here. So who did work? The external agent is going to do work here. I'm going to pull it. And in turn here spring force will be acting. What is x equals 0? This point is defined as x equal to 0. Now I did work. Slowly I'll pull this some, I think elastic band you take it. So when you stretch it, you have to do mechanical work. No? Where do your energy gone? Stored in the elastic band here in the form of elastic potential energy. It will be stored in the form of elastic potential energy. Okay, now let's calculate here now. Work done. So slowly an external agent slowly pulls the block through a distance x. Slowly means from rest to rest it is moved here. So where do then what is work done by external agent? Where to go converted into elastic potential of the spring. So spring force does work here. It does negative work. As it is a conservative force, so potential of the spring must increase here. So now we'll go for work done by spring force should be equal to kx. dw is equal to f into dx. What is dx? You can take like this. Now what is the spring force? Kx into dx. What all work done? Okay, let me keep here. So now this will be kx dx 0 to x. Because initially there was no elongation, now it got elongated by distance x. So this will become kx square by 2. This work done by spring will be stored as potential energy. Now you can ask questions, sir. It does negative work. Yes, in fact it does negative work. We'll do one thing. Then how the work done by spring force, as it is a conservative force, so potential just should increase. Ws equal to minus of delta U, because work done by spring force should be equal to minus delta U. What do you mean by minus delta U? Final energy minus initial energy. What is the initial energy? 0. Final energy is what we are calculating. And how much that final energy is equal to UF. We will substitute here now. So this should be equal to minus kx square is equal to minus of UF minus 0. So what is the final energy stored in the spring? This is a method of bringing. So from where you are writing this equation? Because the spring force is a conservative force. And how work done by conservative force and change in potential related by this particular formula. Hope you can remember. Work done by conservative force equal to minus delta U. That is the reason why I am bringing UF equal to kx square. But don't write negative sign. Why negative sign? Because the spring force will act towards left. The block is having displacement towards right. So what is the angle between them? 180 degree. If you are finding difficult, right? That's all, no? Like this energy. So this will call it as U. So what is the energy stored in the spring? will be kx square. Means if you elongate the spring by x, what is energy stored? Kx square by 2. What is x? X is the elongation here. Energy stored in spring when elongated by length x. Similarly, sir, I am going to compress it. How you explain when it is compressed also? Will it store energy? Yes, yes, the same description. We'll take it. Okay, there's a work done. No? I'll bring it later on. Okay, now action agent will come. It will compress the spring. Who will compress slowly? The action agent. So how the force? Action agent will apply force like this, and the spring force will be acting in this direction. Hey, stop the video. Ananya, stop the video. Okay, what is the compression? So here it is elongated. What about the spring? It is compressed. You are interested, you can show spring force here also. Slowly from rest to rest, it is moved. So I am interested in the energy. So shall we use the same analysis? Yes, the spring force here also now does work, negative work. I'll do it below here for this. Work done, spring force equal to kx. So dw equal to minus fs or fs dx cos 180 or minus kx dx. Work done by the spring force should be equal to, this should be equal to minus kx square by 2. How you define work done by spring force? It's a conservative force, that should be equal to minus delta u. What do you mean by minus delta u? Should be equal to minus of uf minus ui. Initial energy is 0, final energy is what we are calculating. So that should be equal to minus kx square by 2. So therefore finally what is uf equal to? So what is work done by spring force? It does negative work. Potential of spring will increase. So whether you elongate or compress, when spring force does positive work, what will happen to when it does negative work? Potential of spring will increase. That's what I wanted to tell you here now. So in every problem, what is x here now? X is a compression or energy stored in the spring when compressed by a distance x. What is uf now? This you can also call u. What it is? Energy stored in the spring when compressed by length x. Whether you elongate or you compress, there will be energy stored in the spring. If x is the elongation, what is energy stored in the spring? Half kx square. If x is the compression in the spring, what is energy stored in the spring? Will be half kx square. And how work done by the spring force and change in potential are related by this formula. Any reason? Because spring force is a conservative force. Okay, this initial background is there. So the spring force is capable of doing work. It's capable of doing work means it can give energy to the block. Let's see that now. We'll explore few more things. Write down this one. Okay, we'll take the next regarding this is something we had a very example. So we'll do one thing. We'll just